Well, good evening, everyone. Nice to see you here. Um, Today we're going to look at section 15.7. We're still on triple integrals. In fact, there's two situations we haven't covered yet on triple integrals. And this one here is using cylindrical coordinates to calculate them. That's one of the situations we're going to deal with. And we're going to look at what are cylindrical coordinates and how sometimes they can be useful. Essentially, you should use cylindrical coordinates when the thing on the ground is a circle or part of a circle. That's the most usual place that we would do that. And it tends to make calculating the triple integral a lot easier if you do that. And then after that, there's another section that's a little bit smaller, 15.8. And that is the last kind of triple integral where we're going to look at what are called spherical coordinates. And spherical coordinates are not, what's the word? They're not clean, they're a bit clunky, they're kind of messy. But you do use them if the region in space that you're trying to do your triple integral over is something to do with a sphere. So it's either a whole sphere, which is actually the easy one, or maybe the top half of a sphere, or whatever it might be. It tends to be spherical. And you're going to have to change your x, y, z's into this new coordinate system called spherical coordinates. And what that would do is, it's kind of a niche market, but what it would do is allows you to integrate over solid regions that have a spherical look to them, which would be very difficult if you left them in X, Y, Z, for instance. So let's start with the coordinate system, the one that we call, at least, cylindrical coordinates. So what that allows us, whoops, there's a Z. What that allows us to do is imagine we've got a point floating in 3D space. Its coordinates would be X, Y, Z. That's the usual coordinate system. It's the one we use more than any of the others. And if you draw a line from the origin to that point, and then you imagine a vertical line coming down here, maybe going there, we can describe this point using essentially the coordinate system called cylindrical. What it does is it says that distance there is Z, which is how high above the floor is the point P, X, Y, Z. So the Z coordinates are actually the same in both cases. Then you take this guy, I'll try another color scheme, to this point on the floor, this guy here, and that distance is R, and that angle there is theta. So that if we tell you that point, we would tell you R, theta, and Z. So if I told you that R was 5, that theta was 30 degrees, and Z was 10, you would be able to plot that point. And that's essentially what cylindrical coordinates are like. I think they get their name because, can you imagine that there's an infinite cylinder, right? And your guy is somewhere on the surface of that cylinder. So when you do a cylindrical coordinate, you've got a cylinder, and it's basically how high up the point is on the surface of it. And any point on that cylinder would represent an angle theta, and R would be the radius of that cylinder. So to remind you of some formula from way back in the day, X is R cos theta, Y is R sin theta, and X squared plus Y squared equals R squared. They're all very useful. So if I want to convert, and let's show you what it looks like then. If I want to convert a triple integral using X, Y's, and Z's dV over some region E, then I would just convert the X's into R cos theta, the Y's into R sin theta, The z's could stay put as z's, and then I would just integrate them. Now, do you notice that there's an extra r here? It's not a mistake. That extra r comes about that when you change from x, y, z coordinates to cylindrical r, theta, and z coordinates, that you have to compensate for that transformation, and that's what generates this little r. When we go to do change in variables in a later section, I can actually prove to you why that r is there. But right now, you just got to trust it. And it's one of those things that is dead easy to forget. dv, which is dxy dz, is replaced by r, and you can combine them in any order you like. This one I've just decided r dz dr d theta. And we know that x squared plus r squared, y squared is r squared. And that little bit is just basically saying that when you convert this region, E, especially the XY parts of it on the floor, you're going to use R and theta, and it's almost guaranteed that whatever's on the floor is a whole circle or part of the circle. So the first group of questions in cylindrical coordinates are these ones up here. And basically, they're just getting you some algebra practice. This is what they look like. Here is the surface, z equals a function of x and y. Now, that's the nicest one, but you can have x's and y's jumbled up like this. There's another nice one. You can even have that, which if you remember from Calc 3, is a three-dimensional flat line. But all of these can, with a little bit of work at least, can be turned into the equivalent polar format. Now, what you should try and do in every single one of these questions is you want to try, if at all possible, to write it as z equals some function of r and theta. Okay, so there's my first, second, there's my third and fourth one. I'll start with the first one. Z equals x squared plus y squared plus 2xy. Now, when we convert the x and the y, we replace them. Well, the x gets replaced by r cos theta. The y gets replaced by r sin theta. The x gets replaced by r cos theta. And the y gets replaced by r sin theta. So that's pretty much the first line. Every x gets replaced by r cos theta. Every y gets replaced by r sin theta. And then you do style points. You multiply them together. You combine them. You try and make them pretty. You try whatever you can to make them as nice as possible. So this guy is right now r squared cos squared. This one here is r squared sin squared. You multiply all this together, you get 2 r squared sin theta cosine theta. Let's look at these two guys just on their own sum. If I pull out r squared as a common factor, I get that. Agreed? Now, do you recognize that guy as a standard identity? It's probably the only one anybody ever remembers. It's 1. So this is r squared times 1. This guy here, I'm going to rewrite slightly differently. I'm just rearranging the furniture. What on earth is 2 sin theta cosine theta equal to? Because it is equal to something, and it is a trig identity.
Sine 2x.
There we go. So sine of 2 theta. And about the only thing I'm left that I think I can do of any use would be that. So we would consider that guy the equivalent to that. You see, it's now changed from x's and y's to r's and thetas. And it's done in the simplest form. And you really want to do that because you're going to, in later questions, you're going to have to integrate these things. And it's much easier to integrate 1 plus the sine of 2 theta than it would be to integrate, some of these weird stuff. I mean, I wouldn't want to integrate r cos squared on its own. That would be a lot of work, and it's not necessary because with a bit of algebra, it gets used up and it's pretty nice. Now, I could have saved myself a little bit of work here. Whenever I see x squared plus y squared, couldn't I just replace it by r squared without really doing any extra work? Because isn't that a special case? And so we'll use it. And the special case is over here. Okay. Okay, let's look at this second one. Some of these are like homework question, others are ones I've just made up. So we've got this guy, we've got that guy, we've got a z squared, and we get equal to a 1. I'm not going to worry about that z squared right now. I'll take care of that at the end. But I do think I could do a bit of work on this. I know that x squared plus y squared is equal to r squared. So it shouldn't be too much of a jump to realize that 6x squared plus 6y squared gets me 6r squared. Okay. Now, not a lot I can do with that guy except replace it with r cos theta. And then I could do r squared. And I don't want to push my luck. I think that's as good as that's going to get. If I wrote z equals, wouldn't I have to do plus or minus the square root? And I don't think that's really bringing anything to the party. So that's as good as that's going to get. Well, what about a linear one? Right. I have a 9x, take away a 3y, plus a 6z equals 12. Well, there's no shortcuts here, so the x is going to be replaced by r cos theta. The y is going to be replaced by r sin theta. And the 6z is going to stay put as 6z, and I've got that. Well, nothing to combine or do that's much use there, so I won't bother. And what I will do is subtract that fella from both sides and add this guy to both sides. And divide everybody by 6. The reason we're doing this is that you are going to later on be integrating things that look like this or things that look like these guys, and you need to turn them into r's and thetas. So essentially z would become this, for instance. Well, the last one in my list doesn't look too bad, and it's not. But it's not 5 or 5r squared even. And the reason for that is it's a subtraction here. If that was 5x squared plus 5y squared, yeah, but not right now. So that fella is going to become r cos theta squared. And that guy is going to be r sin theta squared. And you end up with this guy. And this guy. I'm going to pull out a common factor. And although that might look like it's as good as style points can be, it's not. If it was cos squared plus sine squared, it would be 1, but it isn't. It's cos squared take away sine squared, but that is a trig identity. Who on earth is that guy?
Cosine 2 theta.
And we are now finished. So you can you imagine you had a triple integral around this guy? You know, where dx, dy, dz going on? Wouldn't it just turn into a triple integral with this guy with drs and dθs going on? So that's kind of the skill set that we're trying to generate here. And that's kind of only taken care of that guy. Before I move on, is there any questions about the conversion stuff? Right, all the x's get turned into r cos theta, all the y's get turned into r sin theta, and use whatever trig identities are appropriate to simplify it as much as possible, and try and do it as a z equals if you can. Are we good to move on? Okay, let's do it. Move on. So now a big chunk of questions is basically, let's use triple integrals. Let's get integration where that is something that we need to be able to do. So here is a triple integral, essentially already done for us. So this question doesn't really require us to do anything except to realize that it's not x, y, and z anymore, right? It's r, theta, and z. So this is what a cylindrical coordinate, typical cylindrical coordinate version looks like, right? It's going to have limits of r, limits on theta, limits on z. They may or may not contain variables like r or theta in them. Some function, in this case it's a very simple one, and then the three guys. So first guy I'm going to do is that guy. Well, if you integrate with respect to z, r, it's essentially a constant, so you get rz. You're going to evaluate it at z equals 0 to z equals r, and then you do the other two guys. Well, if z becomes r, this becomes r squared, z equals nothing, you get nothing, and you are now looking at those two guys. And I'm always on the lookout for making my life easier. These limits of integrations are all numbers, and isn't this function separable? So why don't I just do an integral from 0 to 3 of r squared and multiply it by an integral of 0 to 2 pi of, well, when you use everybody up, you get a 1. This guy is 2 pi. And this guy is 1/3 r cubed. And you get 9 take away 0, so you get 9. 9 times 2 pi, boom, 18 pi. Bit fast there, but it was a pretty straightforward integral, right? There wasn't anything too strange going on. That was kind of a teaser or a warm-up one, since everything you needed to know was there. So if you never even knew what cylindrical coordinates are, couldn't you have done this integral, right? Because you follow the rules of all triple integrals in this case. Now, here's one that has got more going on. I want to do this triple integral. The function is ugly. Well, the square root of x squared plus y squared is typically not going to end well if you're integrating with it. And the region E, the phraseology, once you get used to it, is okay, but essentially what they're telling me here is that there's a cylinder on the floor, a circle on the floor, and the z is cutting it at 1, and underneath it negative z. So what you need to do with these questions here is the first thing that you should do, step 1, is find the limits of integration. And that's for all three variables. Well, this bit here tells me that z goes from -6 to 1. This notation, or this way of phrasing it inside the circle, can you imagine there's a circle on the floor? And that's the circle. And if you need to, you can actually draw a little picture of it. Isn't it a circle radius 5? So a complete circle goes from 0 to 2 pi, and the r value goes from 0 to 5. Are you comfortable with that? The cylinder part generates the floor, and the z is 1 and 6 are basically telling you the top and bottom of this shape. Okay, so step 2 then. Convert your integral. So we're going to convert that guy into polar. I'll do it over here. I have 3 fellas, and I don't know, since they're all numbers, I'm going to go r equals 0 to 5. I'm going to go theta equals 0 to 2 pi. And I'm going to do z equals -6 to z equals 1. That's that bit done. The function that I'm going to convert is the square root of x squared plus y squared. And I'm going to turn that into something that uses r's and thetas. Well, hopefully you recognize that guy as r squared, and the square of r squared is r. So that guy is r. And then the dv guy, well, in case we've forgotten who that guy is, the dv guy gets replaced in any order you like, but that r is important guy. So times an r, a dr, a d theta, and a dz. If I make that a little bit prettier, actually, better be more consistent. That should be z there, right? Okay, that's better. dz, d theta, dr. Okay, let's look at mechanics of this. Would you agree that this is a variable separable situation? All the limits of integrations have numbers, and the function here can be separated. So that means the integral from 0 to 5 of r squared, the integral from 0 to 2 pi of 1, and the integral of z equals -6 to z equals 1 of 1. So if you can separate things, right, any kind of double or triple integral, you should. It tends to make life quicker. This guy is a third x cubed. This guy is 2 pi. Anybody want to tell me what this guy is? Because normally when it's a 1, you can tell what the integral is going to be. What's z equals -6 to z equals 1? What number are you going to get out of that integral?
7.
Yep, 7. Isn't it basically just the difference between the start and the finish, right? How tall it is. This guy is going to be 1/3 5 cubed, which is 125, take away nothing, times a 2 pi, times a 7. Oh, you can finish that, right? Some ugly fraction with a pi at the end. So the key to doing that question was to recognize that the region E gives us the steps. Step 2 would be convert your integral, which is essentially what happened here. And step 3 would be, once you've converted it, just get the answer. right? Just get the numerical value. Now, if you're wondering what this thing is, which is what is 7 of these guys? 7. What's 250? What's 7 250s? 1,750 thirds pi, right? So if you wanted to know what this number is telling you, I want you to imagine that you've got a solid cylinder, right? So Z goes from -1 to 6, so it's up here and it's a big cylinder. And inside this cylinder, every single point has a property equal to this. So this might represent the temperature in that cylinder. So when you calculate this triple integral, what you're basically is adding up all the charge in that cylinder, or the heat energy in that cylinder, or whatever it is, the magnetism in that cylinder. Anything that you can measure, that every point in that cylinder might have a unique value based in its position, and that there decides what it is based on its position. Okay. Next fella. This one. Give me a few seconds. Keep that page there. Okay. Triple integral over some region E. Here is our function. Right. We have a parabola, Z equals 16, take away x squared, take away y squared, and it's in the first octant. So we are going to have to figure out what the limits of integration are for this shape E, the solid shape E, and it's not given to you on a plate anymore. First thing I'm going to do is find out what it looks like on the floor. So if you imagine this shape, it's like a big curved surface and it hits the floor. When it hits the floor, Z equals 0, which means that this guy is equal to 0, which means that, there you go. When this shape here, when this surface hits the floor, Z equals 0, it makes this circle, right? If it keeps on going, it would be different circles, right? But the place on the floor, which is what we're interested in, is this guy. Then they threw this bit in us. Right. Now, the first octant, I mean, in the 3D world, the first octant is actually that guy there. It's the guy where everybody is positive, right? When you do two-dimensional, there are 4 quadrants, right? First, second, third, fourth. But when you're in the 3D world, there are eight octants, and the first one is typically that one, which means that I don't get the whole circle. Isn't that the only piece that we're getting? And that guy is from 0 to 4. Okay, so I now know the r and the theta, the limits of integration for these two. The r goes from 0 to 4. Agreed? Now, what is theta going to be? From where to where? It's very similar to what you do in polar. Think polar.
0 to pi over 2.
Agreed? 0 to pi over 2. Now, the z is a little bit trickier. I'm assuming that it hits the floor because there's no indication that it doesn't. But the other side of the z is this guy. But this z has x's and y's in it, and I don't want x's and y's in it. The z can only have r or theta in it. Are you comfortable with 16 take away x squared minus y squared is the same thing as 16 take away r squared? Can you see where that's coming from? Right. Okay, that is step 1 done. Take the information you've got and find the limits of integration. Check. Step 2 now, set up the integration. Well, it's going to be r equals 0 to r equals 4. Theta equals 0 to pi upon 2. Z equals 0 to z equals 16 take away r squared. X plus y plus z. And to finish with, r dz d theta dr. Now this guy here, right, is okay, right, for that particular guy to have z's in it. It's just no okay for an x and a y. So I hope I've got enough room for this. The x gets replaced by r cos theta. The y gets replaced by r sin theta. And the z is okay. Are we comfortable with what I just did there? We good? Now, this is not that nice, but that's what we've got to live with. So that's what I'm going to work on. So it's going to be r equals 0 to r equals 4. Theta from 0 to pi over 2. Z equals 0 to z equals 16 take away r squared. And all I'm going to do is multiply this out and get a whole load of terms. So I'm going to get that guy, and finally that guy. Right, so I'm essentially just multiplying that through by r. Let's do this integral first. That's basically not got any z's in it, so when you integrate it, you get r squared cos theta times a z. That doesn't have anybody in it, so that's going to get me r squared sin theta times a z. And that guy does have a z in it, so I'm going to have 1/2 r z squared. It's going to be evaluated from z equals 0 to 16 take away r squared. Okay, you plug in a z here, you're going to get r squared. 16 take away r squared, that's the z bit, where cosine theta. If you do this guy times that, you're going to get another r squared. You're going to get 16 take away r squared, and you're going to get a sine theta. If you do this guy times that, you're going to get 1/2 r 16 take away r squared all squared. And then you're just going to have a d theta dr. Okay, I'm trying to see if there's anything I can do here to make my life a little bit easier. And I think there is. I'm going to rearrange my two integrals. I'm going to use these guys together because I can pull out that as a common factor. And then I can do my d theta dr. I'm then going to use this guy as a totally separate integral. And that's going to be 1/2 r 16 take away r squared squared dr. Now, I haven't bothered to put the limits of integration because I'm about to stop here. Isn't that guy variable separable? I know it's horrible, but he's variable separable. And isn't this guy variable separable? And so I could do two separate integrals and add them up at the end. It is not pretty, but it would work. And the answer, I've just had a look at it, is equally not pretty. Okay, let's go through this one again. We had this shape, this integral, over a solid E. E is in the first octant, and it's part of this parabola. To find out what the shape on the floor looked like, I made z equals 0, and I found out it was a circle. But because it was the first octant, it's only this piece of the circle. That gave me the r and theta limits of integration. And z, well, we'll assume it's on the floor to here. And this get turned into 16r squared, which generated this. The x became r cos theta, the y became r sin theta, and the z was okay to leave as a z. That's this bit. The dv gets an r in these guys. And then from this point onwards, it's just really ugly algebra that you have to kind of fight your way through to get an equally ugly answer. Dicks. I just looked at it again. Still don't like the answer. So yeah, let's try this one. Question or version question 7. You're trying to calculate this triple integral. It's this guy here. And E is between x squared plus y squared equals 1, x squared plus y squared equals 16. So you can imagine a big cylinder and a little cylinder. And it's above the xy plane. And it's below z equals y plus 4. So what I'm going to do here is just set up the limits of integration and change the integral, but I can leave the rest to you after that. This piece of information here is very helpful because it allows me to get the xy thing. It's basically a big circle and a little circle. And the guy we're talking about is that guy. And the circle has a radius of 1, and the other circle has a radius of 4. So there's no first octants or y is positive or anything else to restrict it. So I know that r is going to go from 1 to 4. And I know that theta is going to go all the way around, so it's 0 to 2 pi. Now, if you look at z, when they say it's above the xy plane, do you know that's just another name of saying z equals 0? Because the xy plane is z equals 0. And this guy, well, I wish I could keep him as y plus 4, but I can't. I have to turn him into r sine theta, which is what y is, plus 4. So our limits of integration is z from 0 to y, which is this guy, plus 4. So our integral is now going to be r equals 1 to r equals 4, check. Theta equals 0 to 2 pi, check. Z is 0 to r sine theta plus 4. The x minus y becomes r cos theta for the x, take away r sine theta for the y, and the dv becomes an r dz d theta dr. Are you comfortable about this fella with its new limits of integration, the x minus y, and that bit that they always have, the r dz d theta b dr? Are you comfortable where all the pieces are coming from? Since this has variables in it, we must do this integral here first. None of these have a z in it, which is fine. So basically you can take that mess and stick a z in it. The z will turn into this guy, and you will have some really ugly expression with r's and sine thetas and cos thetas and r squared thetas and all those good stuff, but it will be doable. I strongly suspect that it's not going to be variable separable, unfortunately. But let's remind you some of the things that typically happen. Sometimes you have to integrate things like sine squared, right? That could quite easily happen here. If it does, you will use the identity that it's the same thing as that guy. And that guy's a lot easier to do. And if you want to imagine how you would cope with it, that's actually the version of it that you would use. Sometimes you have a cos squared theta to deal with. And that can be converted into this identity. Which in practice would be written down as that guy. And sometimes you have that guy to deal with. Any suggestions how to tackle this third situation? Because there's actually two different ways both work. Anybody got a suggestion how to tackle an integral that ends up looking like that? Now, it might have 5 or 7. All of those might have a 3 or a constant attached to them, even an r, but that won't matter. That's the key part. How would you deal with that? No takers? Calc 2? Use up. Can you use sine theta if you like? Can you use cosine theta? This is one of these nice situations where everybody works, right? Or you could realize that it's that guy and do it that way. But u sub's totally fine. Are we good? Next cell. Again, I'm only going to set the thing up because that's the hardest part. Here we're doing a triple integral of a guy called E or whatever the letter is, x squared dv. And we're told that E is inside a cylinder and it's above z equals 0 and it's below z squared equals 49x squared plus 49y squared. And that is the description of E. So that is the guy that's going to allow me to get my limits of integration. Well, that guy is actually really good because he tells me that I've got a circle radius 2, so I know the r and the theta. Z equals 0, which is nice. And this guy, well, we'll have to do a bit of work on him. X squared plus y squared is r squared, so 49 of them get you 49 r squared. But I don't want to know what z squared is, I want to know what z is. Now, technically speaking, I should be saying plus or minus 7r, but since I know that it's already positive because it's above this guy, I only need that guy. So our integral is going to be from 0 to 2. Theta equals 0 to 2 pi. And finally, z is going to go from 0 to, in this case, 7r. When you do enough of these questions, these two guys on the left here are always going to be numbers, because these two guys on the left are going to be a whole circle or a part of a circle. The only guy that tends to have variables in is the z guy. Now, in this case, I have x squared, which I'm going to call r cos theta squared. The dv is going to be replaced by the r dz d theta dr. And that's going to get me a triple integral, eventually, of r cubed cos squared theta dz d theta dr. And at that point, you would integrate with z. Once you did that, you'll have an integral that only has r and theta in it. And I think this one does variable separable, so that will be a bit nicer to do. But that's as far as I'll take that. Any questions? Any issues? Okay. The last one of this batch coming up. This is a version of question 10. No, I don't want to do 10 yet. Yeah. 10 is a little bit different. 9 is the last one of this batch. No, it's not. Oh, okay. Looks like I covered more than I thought I had. There we are. We've gone over some examples of converting a triple integral into cylindrical coordinates and getting essentially the new integral and solving the problem. The next situation is finding the volume of a solid. Well, here is how you find the volume of a solid. You integrate 1. That will get you the volume of a solid. So we're basically still doing cylindrical coordinates. The region E is going to be something that converts well into cylindrical coordinates, and we'll be integrating 1, which at least that's going to make life a little bit nicer. So let's see what this guy looks like then. Well, the one I kept on saying no to, let's say yes to it now. We're being asked to find the volume of this solid E. And what we know about it is that it lies within a cylinder, x squared plus y squared is 4, and a sphere, which is x squared plus y squared plus z squared equals 25. Okay, oh God, this is going to be hard. If you want to visualize this, can you imagine this is a sphere whose radius is 5? Can you imagine inside this sphere there is a cylinder? If you take this cylinder and you used it to punch a hole through the sphere, you would end up with a shape that would look something like this. It would be a cylinder, but the top part and equally the bottom part wouldn't be a whole half sphere, but wouldn't it be the little bump at the top? This little piece of the sphere here, and this little piece of the sphere here. We are going to find the volume of that weird shape. Okay, so treat it now like a normal question. That guy is our friend because that guy tells me that I've got a circle, radius 2. So I already know, since it's a complete circle, that it goes from here and it goes to here. So far, so good. Now, this fella here is basically the surface, right? The sphere. And this guy here is going to give me the limits on Z. So I'm going to do it over here because I don't have a lot of room. And I'm going to turn that into this guy. Won't x squared and y squared give you r squared? So minus x squared minus y squared gets you minus r squared. Are you comfortable with that? We're good. Now, what will z be? Well, technically z is the square root of this guy. Now, this picture's bad enough, but can you imagine the sphere has half of it above the xy plane and the other half below? So technically there's a plus and minus going on here. So that means z goes from positive 25 take away r squared to negative 25 take away r squared. There is our limits of integration. Are you comfortable with that bit giving me the r and the theta, and this bit giving me the z's? Any questions? I've got a feeling everybody's fallen asleep and I'm talking to myself. You can wave at me if you like. Are we good?
Does that mean that the that this thing is symmetrical about the XY plane?
Yeah, I guess you could just find the top half and double it, couldn't you? Is that
Well,
what you're thinking, John?
Well, wouldn't it mean that the volume's, well, no.
No,
Yeah.
the volume is a physical quantity, so it's always positive.
Okay.
Whether the volume's below the xy or above the xy, it's not like area under a curve where it could be 0 and negative. So I guess what you were saying is, look, if that was true, then this would cancel, and the answer to that would be 0. But it's a physical volume, so it's not going to be 0. But I do like your idea that there's symmetry going on. So if I find that top half and double it, wouldn't that make my integral a little bit easier? So let's use that, although I wasn't intending to, but I like it, so I'm going to do it. The volume is the triple integral of E of 1 dv. Now, originally, that was going to be from r equals 0 to r equals 2, from theta equals 0 to theta equals 2 pi, and then from z equals minus ugly square root to z equals positive ugly square root 1 r dz d theta dr. Well, how about this? The integral from 0 to 2, the integral from 0 to 2 pi, and just do z from 0 to that guy. But double it. That would work, wouldn't it? Just make my life easier. I think having one ugly square root is 10 times better than having 2 ugly square roots, because I can imagine I might end up with 2 really messy pieces, right? Similar, but not exactly the same. So I like that thought. So let's take this one a little bit further. There's your first guy. Now, if you don't like this pulling out 2, just use the original, it'll work. Go 0 to 2 pi. Right, that doesn't have a z in it, so you're going to get rz. It's going to be evaluated from z equals 0 to z equals that guy, and then d theta dr. Well, when you plug in z, you now get r, the square root of 25 take away r squared, minus nothing. Minus nothing. Much nicer, right? D theta dr. And we got lucky. Limits of integration are both numbers. Only has r's in it, so it's separable. So it's going to be 2, the integral from 0 to 2, 1 d theta. And then the integral from 0 to 2 pi, by the way. And the integral from 0 to 2 of r, the square root of 25 take away r squared dr. Right, at this point I'm going to stop. That integral is doable. What method will you use to find it?
U sub.
U sub. And this guy is what, just 2 pi, isn't it? So it's 2 times 2 pi times whatever that ends up being, and you're done. I kind of like the symmetry thing. I wish I'd thought of that. Are we good? Let's see, I think I got one more. I've got it set up here. Yeah, there we go. Okay, sometimes the wording is worse than it really needs to be, but this one definitely is really messy. Find the volume of a solid enclosed by this guy, which happens to be a cone, and this sphere. So I'm not even going to try it. Can you imagine you've got a big sphere, right? And somebody has got a cone inside it, and that cone is coming outwards. Now, when that cone hits the sphere, you're going to have a cone shape with a piece of a sphere stuck to the top of it. So it would almost look like a cone with an ice cream blob on it, right? Very difficult to find the volume of that because it's not half a sphere on the top, isn't it? Just a piece of the curved part where the cone cut through it, right? It wouldn't be very simple to calculate. Yet nonetheless, that's what we're going to have to do here. So I'm looking at these two guys and I'm trying to first figure out, what does the shape look like on the ground, right? So what do you get when this shape hits the ground, right?
You get a circle, right?
Yeah. So all I need to do is figure out what the darn circle is, right? And we're good to go. And fortunately, the circle is a little bit harder to calculate than you might think, because it's essentially going to be the intersection of those two things. Because the circle I'm really interested in is this circle up here. So it's floating above the XY plane, right? And I want to drop it down like I was looking above, staring at it. So I need to know what that circle looks like if you projected it downwards, right? So what I'm going to have to do is figure out using, when does this guy intersect that guy? So that's where it gets a little bit trickier. Well, if z is equal to that, then won't z squared be x squared plus y squared, agreed? If you square both sides. And if I take the other equation, which is this fella, we get that. Are we good? Now, that guy can be z squared. So it means that guy can be z squared as well. So z squared plus z squared is 128. So, oh, wrong way around. X squared plus y squared, z squared can be replaced by x squared plus y squared equals 128. That gets me 2x squared plus 2y squared is 128. That gets me x squared plus y squared equals 64. That circle on the floor had a radius of 8. And how did I find out? I found out when this surface meets up with this surface. So essentially what I had to do is figure out what would be the x and y situation when these two match, right? So square this guy and then replace it here. We got a circle. We are good. That means r goes from 0 to 8. Theta
So,
goes,
just out of curiosity, why didn't you convert everything to r squared? You know, the x squared plus y squared to r squared right away. Like when you were.
oh, I could have. Let's see what that would look like. So z, which is the square root of x squared plus y squared, that one would become r, right? If you want to see the intermediary stage, it would be that. And this guy would be r squared plus z squared equals 128. And then I could replace the z with r, and I'd get r squared plus r squared is 128. So 2r squared would be 128. So r squared would be equal to 64, which means the radius is 8. So I would have found it out that way as well, wouldn't I? Yeah. We know it's a whole circle. So all I was after is what's the radius, right? So if I know r is, I know everything.
Thank you for that.
No, there's a different way of looking at it. Now, we do have some z issues. In fact, we have some major z issues. Z goes from here and z goes from here. Right, so we've kind of half done one of them. That piece of information eventually becomes z equals r. And this one, well, x squared plus y squared plus z squared equals 128. That becomes r squared plus z squared is 128. Z squared is 128, take away r squared. Z is, and we're picking positive because of the story, there is my other z. So my limits of z are going to be from that guy, which is the sphere, to that guy, which is the cone. And I guess I should have put it there, right? There's our limits of integration. The circle on the floor and the z going from the cone to the sphere, right? So if you imagine the z, one part would be on the sphere, and the one underneath it, right? The cone's a bit lower down, would get that one. Are we good with that? Right. So the volume is the triple integral of 1. In our story, r is going to go 0 to 8. Theta is going to go 0 to 2 pi. And z is going to go from r to the square root of 128, take away r squared, 1. Remember the r, dz, d theta, dr. And that is ugly, but it is doable. And what is the answer? Oh God, the answer is ugly. Don't expect pretty answer. Right. Do the Z first, plug in your numbers. You're going to get some R's and thetas. I think actually it's separable, so maybe it's not as bad as I thought. But you're going to have something like R ugly square root, so you're going to have to do another U sub on the R guy. At least the theta guy is going to be 2 pi.
So if they give you a density function, you can
Mhm.
literally find the mass of that cylinder.
Yeah.
And the X and Y and Z
Center of mass, yeah.
center mass, right?
Yeah. In fact, that's going to be one of the questions we'll do later. And you can imagine that we're getting into quite complicated shapes here, where the center of mass is not always that obvious. Even if the object you're making has a constant density, right? So it's all made out of the same steel, right? You still want to know where the center of mass is. And the one I just did there, which is basically an ice cream cone with a blob on the top, right? If I was guessing where the center of mass, I would think by symmetry, wouldn't it be somewhere down that vertical line? But I mean, is it there? Is it quite high up? Is it somewhere on the boundary? Don't know, but I could find out. We good? Let's, I think they got one more. Yeah, they do. And actually, yeah, let's do one more of these ugly guys, the ones I just did. And then we'll do one of your center of mass, John, because that's actually pretty much that guy taken care of, right? So the last one they've got, and I lost it. Okay, I've got it. Oh, okay. Find the volume of the following shape. You've got a guy that looks like this, who evidently is called a paraboloid. So if you can imagine a shape that looks like that, right, there's the z-axis, right, it's a big hat. And it meets up with a cone with the equation 2 lots of x squared plus y squared. So can you imagine a cone intersecting with a shape that looks like a bullet? So you would end up with another ice cream cone story. It would look like that, but with a kind of different kind of scoop on the top, right? The top would be generated by a parabola rather than the sphere. So it's a very similar kind of situation. Well, there's not an awful lot going on here. The first thing I need to do is find out what this thing looks like on the XY plane. Now I can tell that they're going to intersect on a circle, right? Because when cones get cut, they tend to get cut in the form of a circle. And I have this guy, and I have this guy. And somehow or other, we got to make this happen, right? We got to figure out what that would look like. Okay. So if I take the first one, and we're going to use John's idea, because I kind of like it, and I just want to be different. Won't Z equal that guy? Now, if you take the second guy, won't Z be 2R? Do you agree? Square root of that is R. Now, when these two things meet, this Z will be equal to that Z, which means that I'm going to get 2R is equal to 48 take away R squared. And since I know it's a circle, don't I just need to know what R is, right? So let's see what R would be. How about adding an R squared to both sides and taking away our 48 from both sides? And then factoring this thing. God, what would that be? 8 and 6. And that would tell me that R is 6, or R could be -8. Why am I killing the R equals -8 guy and picking the R equals 6 guy? Because it can only be one. What's wrong with the R equals -8?
Is it because
Um,
it would be a negative radius?
Yeah, and we don't have negative radius, right? R is never negative, right? R is a physical thing, so it's a positive. Well, since I know that the floor, the XY plane, the intersection, technically it's a circle floating above the floor, right? But we still want to know what it is because that's our base. Is a circle of radius 6. I now know two of the guys. And Z is this guy and that guy, right? Well, I'm assuming that the parabola is the big guy. Hopefully I got this the right way around. Yeah, I did. That guy. And the cone is the other guy. You happy about where they two came from? Yeah. Now, if I want to find the volume of this shape, it's a triple integral of E, let's call this E, of 1. So it's going to be the integral from R equals 0 to 6, theta equals 0 to 2 pi, and Z equals R to 48 take away R squared. 1. And the dV gets me R dz d theta dr. Okay, we got it.
Real quick, why does the lower limit of z equal r, not 2r?
And that was a very good question, and the answer is I forgot the two.
Oh, okay. Sorry, I want to make sure I was following. Thank you.
No, you know me, it's a good idea to tell us. Right, in this question here, we would just integrate it, right? It would take a lot of time. Can we just call it good? You would finish it yourself. I think the bad one's going to be the Z, isn't it? But I think after that it's variable separable, and that's fine. We can live with that. I'll actually cheat because I've got the answer in front of me. It's 792 pi. Will we just assume that that's true because I don't want to do it? Now, the shape that we're trying to work with kind of looks something like that, right? Let's find its center of mass, just like John was asking earlier. Well, the density function happens to be a constant, k. So the mass of this object will be the triple integral of E k dv, which is k times the triple integral of 1 dv, which is basically k times the volume. And since I already know what the volume is, I can cheat and get the mass without any extra work at all, right? So if you know the mass and the shape has a constant density, don't you just take the mass and multiply it by k, the constant density? Now, to get the center of mass, there's an x, there's a y, and there's a z. And I am going to make these two guys 0. And now I'm going to try and argue in two-dimensional paper why these two guys are 0. If you imagine this shape, but you were flying above it and looking right down on it, wouldn't you see a shape that's basically circular? And then it would drift into a point. Wouldn't it look like a cone going in? Can you imagine visualizing that? Now, my argument for why x bar and y bar are 0 is 1, the density is constant. So it doesn't matter where you are on it, everything weighs the same. So that's a factor we can now ignore. If the density function was symmetric, I would ignore it for the same reason, right? I could get away with both being the same. Would you agree that that guy is 0, 0? So the only guy in town I need to worry about is Z bar, which is basically, if you imagine this being the z-axis, where along this axis would the center of mass be? Does that make sense? That's probably where it's going to be, right? Somewhere right up the center of the shape, but you know, is it height 2, 4, 6, 8? Well, where's it going to be? Well, if you want to find z bar, it's 1 over the mass, the triple integral, right, of E, times x, the density function, dv, right? That's your starting point. Right, that's how you get, when x, oh, nobody caught me. There, z, right? If it was x bar, which is where my brain was thinking, wouldn't that be x density? If it was y bar, it'd be y density. Right? Now, I already know what the mass is. So that's taken care of. I've already figured out these limits of integration. We already figured them out as r equals 0 to 6, theta equals 0 to 2 pi, and z equals 2r to 48 take away r squared. Z, k, and the dv becomes r dz d theta dr. K is a constant. I'm going to pull it outside. And as long as it's just a number, a constant, you're allowed to do that. And I'm going to leave myself with zr dz d theta dr. And then I would integrate that guy. And we would get, oh, by the way, the k's cancel. And I'd have a 0 to 6 and a 0 to 2 pi. And this guy becomes 1/2 z squared r evaluated at these two places.
Just out of curiosity, if you work through the first part of this, get the volume,
Mm-hmm.
and then now you're adding one variable to that, all that work.
Yeah.
And I haven't
But
done a lot
they-
of these. I haven't done a lot of these yet, so it seems like, wow, now I got another whole freaking thing to do again.
Yeah, that's pretty much it.
So
You
there's
do
no
have-
way to shorten it. Like, there's no similarity to the second calc at all.
Unfortunately, no. You would hope there was, but not really. Analogy. Imagine you integrated x squared, right? You get 1/3 x cubed.
Yeah.
Imagine you multiplied it by another x, which would be x cubed. You get 1/4 x to the 4. There's not an awful lot of, there's not enough things going on there that there's a pattern that you could use to speed things up. So the bottom line is, yeah, you got an even different but similar looking, but different enough that you have to do it from scratch. Now this guy is pretty much as far as I want to go in this fella. It's going to be 1/2 48 take away r squared times r d theta dr. Right, at least that's variable separable, right? So you could at least pull out the d theta guy, but that's just one ugly polynomial, isn't it? And you'll trust me because I've got the answer in front of me. It's 234/11ths when you're finished. So the center of mass would be 0, 0, 234/11ths. So what's that about? 11, 12, 30. It's just a little bit above 13 units. So you imagine that cone and you went 13 units above it. Unless I could figure out how tall the cone was, I could tell you, but at least I know it's 0, 0, about 13 and a bit. Yeah, there is no, unfortunately, we love shortcuts. I do too, but just sometimes they don't exist. Question 13 is similar to that one, so good luck when you do it. Right, we got one last group of questions, and that's this piece finished. I'm going to, I think I'll mention it now because my memory I'll forget. Everybody here was given or sent out a printout of their score, right? So it was sent out yesterday evening. The solutions do exist. I've got them actually. So at the end of today, if you specifically just want to know about one question, I can do that. The reason I don't want to publish them yet is that there's one student who still hasn't taken the midterm for a particular reason. And so it's not a good idea to put solutions to things up, especially if I'm going to be using that with that person. So if you can wait until that happens, you can have a look at all of them. But you know, so you don't get bugged, like question 5's driving me crazy, I need to know. Hang about at the end and I'll go over it with you, right? Or whatever it might be. Second thing is that check that it's accurate, because, you know, I might have put 48 down, because I know one person sent me an email essentially saying, this is what you said, but I got that, and I went back and he was telling the truth. It was exactly what you said, so I changed it. And lastly, if you look at your online test, because that's the only place right now that can have any great effect on your grade, your grade can only be better than what that says. What am I getting at? If you've missed totally an online test, right, there's a 0 right now, that will disappear. So right now, that's worth about 5%. So if you just added on 5% to your grade for 1, God forbid you missed 2, but if you had missed 2 and you make sure you do all of them from now on, that will also get kicked out. So that would increase your grade by another 5. If you've done an online test and it's pretty horrible and you know that you're probably going to do better in, you know, one of the others, that will get kicked out. But that's probably only going to be worth maybe 2% to your grade. So if you've got a really bad one, if you add 2% to your grade, that's probably a more realistic idea of what you've got. Okay, let's finish these last guys off, and then I'll talk a little bit what's coming after that and call it good. Here we're given some integral in x, y's, and z's, and they are absolutely horrible. So you've got an xz, that's not horrible, but the limits of integration are, and you've got a dz, a dx, and a dy. And the limits of integration are y equals -9 to 9, x equals negative the square root of 81 take away y squared to positive 81 take away y squared. And then I'll change color on this one. The z limits go from the square root of x squared plus y squared to z equals 10. Now, if you left that guy the way it is right now, can you kind of, just looking at it, can you see this is not going to end well, right? These limits of integrations are going to make it so difficult, if not impossible to do, that you'd say, ain't going to happen, right? Integration is, you know, it's quite easy to make an integral so hard it's impossible to do, right? And this would definitely be that. So what we're going to do is take this fella and convert it into cylindrical coordinates. And when you do that, it'll turn into a different integral that's the same as that, so its answer is going to be the same, but it is much easier to do. So the first thing you do is you focus on these two guys here, the red ones. Now, if you take x equals the square root of 81 take away y squared, and you take into account these two guys, what you're looking at is the floor, right? The x and y. Now, that might not look like anybody you can recognize, but with a little bit of math, do you see it's an entire circle? Not only is it an entire circle, isn't the radius 9? And this guy says -9 to 9. That's important because in this question, what that basically tells me is it's a full circle. Can you pretend for a minute that said y equals 0 to 9, right? Then wouldn't our region only be the top half of the circle? Right. So, full circle, radius 9. So r goes from 0 to 9. Theta goes from 0 to 2 pi because it's a full circle. And z is actually pretty much what you see is what you're going to get. On this side, 10. On this side, what will that turn into? Because we've done enough of these tonight that we should know that that's actually much nicer when you go polar. What's the square root of x squared plus y squared going to be when you go polar? Or I should say cylindrical, but it really is polar. Any takers? Or are you comfortable about how this system became that? Right. So use the x's and y's to figure out how much of a circle you've got. In this case, all of it, and what the radius is. And then these guys just get turned into something with r's or thetas in it. Well, we're halfway there. So it's going to be the integral from r equals 0. And I said that guy there is 9 to 9. Theta is going to go from 0 to 2 pi. And z is going to go from r to 10. X is going to be turned into r cos theta. Z is going to be called z. And the dz, dx, dy, basically your dv, gets an r, dz, d theta, dr. Don't forget the r. That's a common mistake, right? The dx, dy by dz, any combination, when you go cylindrical, you get an extra r because you do, right? Right now, you do because I tell you do. Later on, I can prove it to you why. So I'm now going to go 0, 9, 0, 2 pi, r to 10. This, I'm going to get 2r squared cosine theta z, dz, d theta, dr. Let's do this piece. Well, z's the only variable in town. All of this is just a constant. So add 1 to the power, divide by the new power. And you get that guy. Evaluated from z equals r to z equals 10. Plug in 10 here, you get 100. So that's going to be 100 r squared cos theta. Plug in r here, you're going to get, oops, take away, plug in r here, you're going to get an r to the 4 cosine theta, d theta, dr. Now, in a question like this, I suggest that you break it into 2 distinct pieces.
Sorry, quick question again.
Yes.
Where does the 2 in the 2r squared cosine theta come from?
Where did the 2 come from? Oh, That's a good question. Where did it come from? Did I just put it in because I like it?
Trying to.
I just put it in because I like it,
Oh, okay.
which of course means that's a half now, which is fine. Which means that's a 5, and that's going to give a half in it. So there we go. Right, and this guy, I think my brain was thinking earlier on, remember that 2R that we had in a previous question? I think my brain was still thinking there somehow. Right, split it into 2 guys. Isn't that variable separable? Isn't that a different variable separable? And I think that's less work than trying to keep it together as one single integral. So get that guy, take away that guy, and you are good to go. Apart from the weird 2, I have no idea where it came from. We are good. Okay. One last one. This last one, I'm not going to do quite as much. This is a version of 15. So we have x equals -5 to x equals 5. We have y equals 0 to y equals the square root of 25 take away x squared. And we have z equals 0 to z equals 25 take away x squared take away y squared. And pretty nondescript function, dz, dy, dx. These 2 guys here, they're going to tell me the xy plane. They're going to tell me the floor. If I take this fella, just like the last time, because everything's going to pretty much end up being a circle, I get this guy. If you square both sides. And if you add x squared to both sides, you get a circle radius 5, which is true. Oh, wait a minute. The other side isn't minus that square root, isn't it 0? So I don't get a whole circle. Don't I only get a circle that has a positive y in it? I get the half on the top. Does that make sense? Now, does it match these guys? Yes, it does. So this is the floor, right? Half a circle. Just for argument's sake, suppose this guy here had said x equals 0 to x equals 5. Wouldn't I now only end up with a quarter of a circle? That makes sense. So the limits of both limits of integration tell you something. Now, since it's a top half, the r is okay because it's still a radius of 5. The theta, however, well, it's going to start here and curve all the way to just there. So it's going to be 0 to pi. Okay, I think we're ready. We're going to do r equals 0 to r equals 5. Theta equals 0 to pi. Z equals 0 to that guy. And I think we've done enough of those guys to recognize 25 take away r squared. And I think we've done enough of these guys to realize that that's r. And then these guys get an r, dz, d theta, dr. Okay, call that guy r squared, integrate with respect to z. You'll be left with the next 2 guys. I'm pretty sure the variables are separable. And off you go. And according to what I have in front of me, oops, it's 1250 1250 pi over 3. It's quite big, but probably these guys here are causing the thing to be large. Okay, that's it. Any questions? Anything for the good of business? Okay, now finishing a little bit early today because well, that's how long it took to cover the stuff. Plus, I want to hang about at the end for anybody who's got questions. But we're kind of crunched when you know when we use up a day for a midterm. I can't really afford not to do that day. So what I'm going to be doing is I'm just going to make a video for the next section, which is 15.8, and it's basically triple integrals using spherical coordinates. And I'll just put that online as soon as I get it done, which will be, well, actually I've got a meeting tomorrow, so it won't be until Thursday evening. And that will be that covered. So you just have to watch that video when you have time. And that will get us through this week's work, which is 15.7 and 15.8.